Wonderful. Okay. Thank you for coming. Thank you. So good to see so many of you on what is becoming a Wednesday tradition of cloudy evenings. I'm so sorry. I think the clouds just hate Wednesdays. We had lovely seeing last night. I'm sure it's going to be like being clear tomorrow. But we have a good evening of astronomy for you either way. So after our speaker, we're going to have the traditional tea and biscuits as a sort of consolation prize, and then we're going to be back in here from a talk from the CAA all about meteorites and shooting stars. So I'll introduce our headline speaker. So we have Michael Rigaud, who is our colloquium speaker visiting the department from Lyon, who's giving a scientific talk to us tomorrow. He kindly volunteered to give a public talk all about his research, which is all about how we measure the universe using exploding stars. So yeah, give him a big hand, Michael.
Thank you very much. Okay. Can you hear me correctly? Yeah? Okay. So I hope you will not fall asleep. It's getting very dark now. But it's better to look at stars. So I'm going to talk today about type 1a supernovae and how we can use that to measure the expansion rate of the universe. So let's start first by looking at this image. And so this is an image you famously know, I think now, from GWST. And what you see here is basically what you will see if you hold a grain of sand or salt from your arm like that, and you will point in any direction in the sky. And this is basically what you have behind, very far. And all of those things you see here are galaxies like that, all those points, except the one where you do see the spikes like that, those are stars. And so what we do with type 1a supernovae is that we try to observe the sky to measure the universe. But when you look at the sky from where, in France, for instance, so you know where that is, and basically what you see from major cities, so apparently not from here, but from major city, is that you basically see the moon and a few other things. Just to get a sense of distances, this is at scale. So this is Earth, and this is the moon at scale with distance n size. So you see it's very far, and it takes about 1 second from the light from the moon to reach us. If we were to go there with some spaceships, the best we have right now, it will take about 10 hours to reach the moon. And it's a few months to go to Mars, for instance. So this gives an idea of scale. And when we look at from other places, like here, I think, or here is where I have spent a lot of time when I was a kid. This is in Ardèche, in south of France. It's very nice, very lovely. It's basically in the middle of nowhere. You can start to see stars. And you can see planets, and just to give an idea of how far things are, again, so we are here, and the light that goes from the sun to reach us, it takes about 8 minutes. And to go as far as the last planet, it will take about 4 hours for the light. For us, it will take 12 years with this starship we had access to. So really things are quite far. And this is only the very neighbor. This is where we are. This is really our solar system. But there are places where we can go on Earth where we can have access to amazing sky, and this is in Chile. And you see here that all the things you see here are mostly stars. There is maybe a few galaxies that are hard to find where they are, apart from obviously the big one here, which is our own galaxy, which is the Milky Way. And to get a sense of all the stars that you can see from very nice sites, either in Ardèche or here, hopefully when it's not cloudy, and in these amazing sites, the nearest stars we have is about 4 light years away from us. So if we have the same starship to go there, it will take about 100,000 years to go there. Just to get a sense, human has invented agriculture 10,000 years ago. So it would have been 10 times longer than that. We had to invent starship, send the first human there, and we will reach the first star. So this gives an idea of if we destroy our own planet, for instance, it's hard to find another one where we can live from another solar system with the technology we have so far. So this is an idea of what we see. But when we do cosmology, we don't look at stars. We look at the universe as a whole. And so we come back to this first initial picture, and we are not looking at individual galaxies where you have all the stars I was showing you from our own Milky Way. We look at how galaxies behave. And when we look at a picture like that, like the one you see behind your arm like that all the time, we have the feeling that this universe is static. Like this is how it is, and this is how it has always been. And actually, this is not quite true. So it has been discovered, it's actually, well, it's very bright. So it has been discovered, now it's about 100 years ago, that we've seen, oh sorry, it's in French, but you can guess that. So this is distance from Earth. Sorry, I thought I switched all of that to English. Usually I'm giving this talk in French, as you can guess. And so this is distance from Earth, and this is how fast things are moving away from us, apparently. And you have this very famous relation that have been discovered by Lemaitre and Hubble about 100 years ago. And we see that objects that are far away from us are also apparently moving fast from us. The recession speed is important. It's like everything are going further away from us. So it doesn't mean that we are in the center of the universe, because we are not, and potentially nothing is. But what it means is that the distance between galaxies are increasing all the time. And so it's actually the space-time itself that is increasing, which means that basically between two galaxies, when you had, I don't know, 1 meter, for instance, obviously it's not in meter, right? But the 1 meter becomes 1.5 meter in the space-time. So this is a space-time increasing. And so it will mean that every meter becomes 1.5 meter, which means that the effective distances of galaxies is increasing. But obviously, the galaxies that are really far away from us get more of those 1 meters that becomes 1.5 meter. And so the effect of this increase is much stronger for galaxies that are far away from us. This is actually what we see here. So what I'm telling you here is that galaxies, right now, we see that we've seen 100 years ago, that galaxies are moving away from each other. But when we think about it, it will mean that in the past, they used to be closer to each other, right? So there is nothing magical in what I'm saying. But when we think that further and further, at some point, the galaxies potentially were very close to each other, like overlapping each other. And at that moment, they were not galaxies anymore. And the same thing for particles and everything. And this is the beginning of the theory of the Big Bang you may have heard about. This is only coming from the fact that we know now that galaxies are increasing, and that now the distance between galaxies is increasing. And so they used to be closer in the past. And in this graph, I'm showing you what we can understand from that. So this is showing you what I just said. This is where we are now, and this is the past. And this is the relative size of the universe. So 1 is typically the typical distance of galaxies today. And in the past, they used to be closer to each other until this moment which is called 0, where everything was so much overlapped. The universe was infinitely dense. It doesn't mean that it was small, because it could have been still infinitely big, but infinitely dense. Okay, that's very weird, but that's the way it is. And so the curve you see here is now a different model of the universe for how things can happen in the future. So the data I was showing you, the expansion of the universe today, is the data from Hubble. This is this small patch here in the sky that you see, the small black dot here, that shows that the universe is in expansion. But how fast it was in expansion as a function of time gives you an information of what composes the universe. And so the curve I'm showing you here is different density of galaxies in the universe. And this one here is what we call the critical density. So if we start from the initial moment here, where we're in the Big Bang, then the universe is in expansion, so all galaxies are moving away from each other. But we can imagine that the gravity will slow down this expansion at some point. So galaxies are moving away from each other, and because there is a gravitational attraction that attracts galaxies to each other, we can imagine that it goes like that, it expands, and at some point gravity wins, and it falls back on top of each other. And galaxies, because of gravity, are going to get closer again from each other, fighting this expansion from the universe. This will be all the part which is in this blue area here, with a critical density stronger than 1. If the critical density is smaller than 1, it will mean that in comparison to the initial expansion of the universe, the density of galaxies is not strong enough, and that the universe would be in expansion forever. Another way to see that is like, if I'm throwing a stone in the sky, the stone will come back to the ground, right? But if someone is very strong, like Superman strong, you can throw the stone away, and the stone will go in orbit and never come back again. This is kind of the same thing. And you see that actually, if we have enough data in the past to fill this curve here, looking in the past, we can know in which curve we are and discover what is the fate of the universe. Will it expand forever, or will it collapse back on each other? And to do that, we need to be able to measure this kind of measurement, time and relative size, for very long distances, very far in the past. So to measure those two things, we're going to use two quantities, the redshift and the brightness or distances. So the first one, the redshift, we're going to get it from spectroscopy. And so if you look at if you disperse the light here, you may see, if you have a spectrograph, that you have absorption line. And if you have an expansion of the universe, I'll show you that those lines are moving. So what I'm talking about here is this very simple concept called redshift. So the redshift is that you have a galaxy here that emits, like most of the time, you have hydrogen in the universe. So you have an emission from hydrogen lines. And so the photons fly from this galaxy to us. We are in this galaxy. But the time it takes for the photons to reach us, the universe is expanding. I told you the universe is expanding, and distance between galaxies are very far away from each other. Sorry, distances are very important. And so the time the photon comes to us, the universe is expanding, and this stretches the wavelengths of the photon. And if a photon gets a longer wavelength, it becomes effectively redder. And so this is what we see here. You see that in the case of the sun, we will have this kind of absorption features. And if we look at a distant galaxy, we'll see that all the lines are shifted, in that case by 5%. 5% will mean that by the moment where the stars from this distant galaxy have emitted light, and the moment when it reached us, all the photons get stretched by 5%. It will mean that the universe is 5% larger today than it was when the star has emitted this light. But it doesn't tell us if the universe has been doing something like that, as expansion or the smooth expansion. But if we have this information for many distances, then we can reconstruct the history of the expansion of the universe. And to get this second information, so in that case, you have here the stretch, how much the light appears red, and you need this second information here to fill the curve. And this is coming from distances, and this is where I'm talking about type 1a supernovae. So type 1a supernovae is a very strange star that is exploding. It's an event of a star exploding. I'll show you next slide. But what is particular about type 1a supernovae is this explosion is very common in the sense that it's very alike to each other. They are very objects that look a lot like each other, which means that their peak brightness is nearly always the same. And because we have an object that is always exploding roughly the same way, then if something is appearing fainter, it means that it's further away from us. And so this is the same idea behind, I don't have the name in English, sorry. Well, you come back to me. Basically, it's what we call a standard candle, a lighthouse. Exactly, we say it's a lighthouse, right, for boats, right? Okay. So it's the same idea behind a lighthouse. If the light is really bright, it means that you have to stop the boat, otherwise you're going to destroy your boat. But if the light is very far, then you know you have some time. Okay, that's the same idea for standard candle with type 1a supernovae. If something appears very bright, it means it's very close, because you know that something much fainter, because intrinsically the same. If it's much fainter, it means it's further away from each other. And so this is what is particular with type 1a supernovae. It's one of the standard candles. There is a few standard candles in the universe, like Cepheids and others. But what is unique about type 1a supernovae is that not only they are standard, but also they are extremely bright. They are as bright when they explode as an entire galaxy. And a galaxy is basically 10 to the 10, so 10 with 10 zeros after, sun-like stars. So it looks like that. So you have a galaxy where you have many stars, but at some point you have one of them, it's actually a white dwarf, that explodes and it brights like that. And the history of this brightness forms what we call a light curve. So you have like very undetectable flux, like basically the sun. And then it blows up, and in 2 weeks, it becomes 10 to the 10 times brighter. So all the energy of the stars is blown up, and you have a lot of energy released as photons. And then it goes down in a couple of months. And you have here how it looks in different bands. So if you look at it in the G band, or in the I band, or in the V band, so the green, red, or infrared, for instance. Okay? What matters here is that this peak brightness here is roughly always the same, and it's extremely bright. And so if we now come back to this plot here, we see that we can compare if you have access to the color of the photons, you know how much the universe has expanded. And if you have access to the brightness of your supernovae, you know how far this thing was. And so in summary, this is what we can do with type 1a supernovae. This is an illustration where you see in this small animation a supernovae happening here. This is a fake galaxy, but then it's real data. And then you'll see it looks like real data after. Exactly. And then while the photons from this supernovae is traveling to us, the supernovae light becomes dimmer and dimmer and dimmer because it's super far away from us. And at the same time, the photon gets redder and redder and redder. And by measuring how red and faint the object is, we can measure how fast the universe has expanded in the time it took for the light to come to us. And in that case, it's here. And what is remarkable, talking about time, is that when the supernovae exploded, Earth was not there yet. The universe, the sun was still in formation. And so it takes all that time for the light to reach us. And when we do that for about 1,000 supernovae, we see all of those points. So the different colors are different instruments used to measure the supernovae. And the further away you go from us, the bigger the mirror you need, obviously. And you can remark one thing here. So you have all those colors, and the black points here are showing you the average when you mean all those supernovae you have, because you have some noise in the measurement. And there are two things you have to see in this figure. The first obvious one is that the line here goes to, there is no curve that goes through that. It's completely off all the curves. And the other thing you see is that we are definitely in the white area here. So we know that the universe is expanding forever, but there is something wrong here because it goes through no model here. And so what is missing is dark energy. Dark energy is this additional component that we now need to have in our model that we can add in the Einstein's equation for general relativity that will accelerate the expansion of the universe. It plays an anti-gravity effect. So it's not only that the galaxies are moving away from each other, but how fast they move away from each other is getting stronger and stronger with time. It's like if void wanted to push, and then if it pushes, there is more void, and so the void becomes stronger to push again. This is how it looks, and it's very weird. But if you do that, you have a curve that goes very well through that, and this is this curve here. And this curve here shows you that we have 70% of the energy content of today is made of this dark energy. And this was discovered about 25 years ago and awarded the Nobel Prize in 2011 with 100 of those supernovae. In this figure you see here, it's about 1,000 of those. So we can start probing the properties of this dark energy. And so we are in a universe made of 70% of dark energy and 30% of matter, of which the vast majority is actually dark matter, which is completely another talk here. And type 1a supernovae don't distinguish normal matter from dark matter. And so this is where we are. And then I'm going to show you in the next few slides the thing I'm working on with right now. It's another survey that we have that is able to look for the sky to see this evolution of the light curves I was showing you, to see exploding stars like type 1a supernovae. And the one I'm working with is called ZTF, this one with this very large field of view. If you recognize this is Orion. And so Orion is pretty big, right? And so this is a major survey with a very large field of view. But it's only on 2-ish meter telescope. And the one that is starting to arrive, that we're going to hear a lot about in the next few years, is LSST, which also has this very large field of view, but sitting on an 8-meter telescope, so you can see much deeper. But with ZTF, we are able to scan the entire sky more than once a night because we have this large field of view. So we take exposure of 30 seconds, and then we move to the next field, and we do like that. We've been doing that for 8 years now, and we scan the sky every night entirely. And so we detect all supernovae that explode in the northern sky. So this is how it's sitting in California. And so this is how it looks. Does it work? Yeah. So we go from this is a very, very small fraction of the detector, where you see here you have stars, and here you have a galaxy, and this point here is a type 1a supernovae that arrives and that goes away. And so for instance, it was not there, and then it explodes, and you see this transit appearing, and you have to measure the flux of this, and there is an entire work of data processing to extract exactly the flux of the supernovae and not of the background galaxies, and accounting for all defects, all the clouds and everything. And so this is how we actually do measure type 1a supernovae, and with ZTF we have observed about 3,000 of them already that are all at near distances. So it's a factor of 10 more than everything have been acquired in the last 10 years or 20 years actually in these same distances. But what I would like to insist for, which is an important component of our work, is that it's all the data processing that goes with that. Just to give you an example, one simple example, there is about one type 1a supernovae every 1,000 years per galaxy. So if you just look at one galaxy, it will take 1,000 of years for you to have a type 1a supernovae. So obviously we don't do that. we have to scan a large volume of sky to find those type 1a supernovae. And this is why it was so hard before ZTF to observe a large volume of sky, because ZTF has a uniquely large field of view that no one had before. But just to give you a sense, ZTF finds about one supernovae every open hour of time of observing. And in comparison, we find 300,000 what we call alerts, so moving stuff, blinking effects in the camera every 30 seconds. And so we have to sort out all of those alerts from the really rare type 1a supernovae that are hidden in there. And this is a kind of job we do with big computers. With that, we have observed today, and we just released about 3,000 type 1a supernovae, and this color shows you how many you have per patch of the sky, and this gray band here is the Milky Way. You don't see anything through the Milky Way. And it's all white here because it's Earth, and you don't see in the south if your telescope is in the north. So with all of the supernovae, we try to understand what we've discovered 30 years ago, that we are in a universe with 30% of matter and 70% of dark energy. And our job is to try to understand the properties of this dark energy. That's my final slide. Thank you very much.
Thank you so much, Mikhail. Do we have any questions for the speaker? Which is swap sides, usually in the middle. Any questions? You've blown everyone's mind thoroughly.
Yeah, yes, they were all asleep, right? We don't know.
So, what is a type 1? So, type 1a supernova?
Actually, we don't know. So that's a catch. So it would have been a much longer talk. But so we know things. We know it's a type. We know it's a wide from the evolution of the light curve and from spectra we can also obtain from those supernovae. We know that type 1a supernovae is an explosion of a white dwarf, and we know that white dwarfs have a limit, what we call the Chandrasekhar limit. They have a maximal size above which they are not stable anymore and they blow up. But what we know is that we had to have a normal white dwarf that existed, then somehow accreted mass to get bigger and bigger and then blow up. But how it accretes mass, we don't quite know. We're not sure. There are many different flavors. How then, while it accretes mass, what is the detail of this explosion? Is it like everything blows up, or you have different areas that blows up? Is it symmetric? Is it not symmetric? How is the composition of the white dwarf and the composition of the donor affect the way it explodes? All of that we quite don't know. So it's an empirical tool, in the sense that we have observed that they are very all the same. We have observed that for the thing that the same redshift, they have the same distance, what we call the scatter in the Hubble diagram. So it's very small. So this is an empirical probe that we use.
More questions? Yes, please.
How did you become interested in astronomy and this topic in particular?
So that's two different questions. So I don't know how I think I've been interested in astronomy forever. I mean, looking at the sky from going on vacation where we do see the sky, so not from big cities. It was always amazed me how it was. Then at the end, so I knew I wanted to do physics, and so I went to physics schools. And then when it was time to obtain to start a PhD, I wanted to go more in computing because I like coding a lot. And so I wanted to go more in computing / theory because most of the students, they want to do theory because they think they can reinvent the universe and everything. But fortunately, they said no to me for that. and so another person I knew was like, okay, I'm doing type 1 supernovae. We have an opening PhD. Do you want to join? I'm like, sure. And so this is how I became a researcher in type 1 supernovae cosmology. So it happens that when you are starting your PhD, you just don't know what you have to do because the field is too complex. You can't guess. So you have to trust the advisor to say, okay, I think this is a good topic. Try. So yeah.
Yes, please.
Am I right in thinking the rate at which the universe is expanding is accelerating?
Yes.
And it's not only the distance between galaxies that's getting bigger, but also the distances at a microscopic scale would be getting bigger as well, like the solar system would be getting bigger? No.
So that's an excellent question. So what is expanding is actually the space-time metric of the universe.
Yeah.
Okay. But the gravity, because there is a connection between matter or energy and the space-time, and energy or matter is deforming the space-time. And so the way you should see it is that when you have a lot of things, high density, like in a galaxy, or even like in a galaxy cluster, the gravity is so strong that it maintains the structure of space-time bounded this way. And so it's only when the things are very distant, when the density is very low, that this is unbounded, and then the space-time can increase. But galaxy clusters are actually super rare, and so distances between galaxies are usually very strong, very lot of void. And so in very low density area, then the expansion wins. But within galaxy cluster even, this is bounded. So what I'm saying here is for cases for normal dark energy. So since we just don't know what that is, there are also theories where you have different kind of dark energy that may also unbound this kind of galaxies altogether. But in what we think right now, or the standard model, I would say, you have this bounding effect that holds galaxies together. So for us, it doesn't affect us. It doesn't affect the solar system. It doesn't affect the galaxy.
Thank you. There's an amazing, I don't know if have you ever seen Annie Hall? There's an amazing scene in Annie Hall.
Oh yeah? It was long ago, yeah.
The main character is very depressed and doesn't want to get out of bed. And his mother says, well, why don't you want to get out of bed? And he says, I'm so depressed, the universe is expanding and it's just bumming me out. And his mother says, no, you don't live in the universe, you live in Brooklyn. He said, and Brooklyn is not expanding.
Exactly.
Right.
She's right, she was definitely right.
She's exactly right.
Yes, it's no excuse. I think there is a question over there.
Yes, thank you.
I was wondering what the theories are around the significance of this dark energy. What can you say about that?
So, the standard model is that it's a what we call a cosmological constant. So this is where we are so far. So in Einstein's equation, so it becomes technical, but in Einstein's equation, actually Einstein's equations themselves that connects how geometry of the space-time is connected to matter that compose it, and it's only the derivative of that is well defined. Okay. What I'm saying here is that because from going to the derivative to the main equation, there is you have to do an integral. And when you do that, there is a constant that may arrive. What I'm saying is that Einstein's equations are defined at a constant term. So you can always have a constant term, and this is still correct. And there is no reason to imagine this is zero, and there is no reason to imagine this is not zero. So we just don't know, right? And if this is you can actually have a constant that mimics exactly that. So it will be, but the issue with that is that if it's on one side of the equation, it means that it's a properties of geometry of space-time of the universe. But if you put it on the other side of the equation, in the matter side, then it means that there is something, an energy fluid, that will create this expansion that affects geometry. And because it's a constant, you can just move it, right? But the physical interpretation is completely different. And so when we say here is 70% of the universe constant or content is that when you move it to the matter side or the energy side. But it's really puzzling because there is physically no reason to have that. And then something even more puzzling for our universe is that it means that you create energy in the universe. So for instance, the fact that you don't create energy that is supposed to be conserved, actually it doesn't work in the universe. Only on the universe. So it's a really niche effect. But yeah, the energy is not conserved in the universe.
Yes, got it. One more. Two more. Yes.
Oh, sorry, you're here.
Okay, if dark energy is theorized by moving this constant around in this equation, we only think it's there if we move this constant to one side of the equation, and that drives an expansion of the universe. Dark matter is
So dark matter.
contraction.
Yes, so dark matter is different. So I mean, there is a lot of confusion because they have the same dark. Dark is we are in the dark, right? It's yeah, and so the thing that dark matter is called dark because we know it's a particle. We know it from the shape of the galaxy, but mostly now from the features of the CMB. So I haven't talked about that here. But from what happens, how we explain observation of the first light in the universe, that was free. Dark matter is a particle, that's almost for sure. I mean, nothing's for sure because we don't quite know what that is, but in the standard model, it's a particle, and it's dark because it doesn't interact with light. It's only for that. So everything we are used to, the fact that we see each other, the fact that my hand doesn't go through this screen, all of that is light interaction. It's electroweak physics. Dark matter doesn't know light, doesn't interact with light. And so we have almost no experience with that because the way we can interact with this particle doesn't exist. But we see its gravitational effect because it has a mass. And so we see, when we can see gravitational effects, we can see it. So in the galaxy where you have a lot of matter, we see, for instance, for the galaxy rotation because we detect it through its gravitational effect only. Dark energy is not the same scale. It's not within galaxies. It's within very vast distances, and it's very weak in comparison. And it's potential, and it's likely not a particle.
Okay, so let's do one last question at the back.
Yeah, you mentioned the difference between infinitely small and infinitely dense. Can you elaborate on that? And does it relate to our thoughts on whether the universe beyond the invisible universe is finite or infinite?
So what we know from the CMB, what we know from observations, is that the universe has went through a phase of being extremely dense and extremely hot. The extremely hot comes from the fact that it was extremely dense. So particles were bumping on each other, making it very hot. So we see light from that from the CMB. We have proof of that, direct proof of that. And then we know that from this very dense, where you didn't have any particles, it was just fundamental particles. It was not even atom yet, right? So we have proof of that. Then what happens and so it was the universe infinitely dense. And then we know that this expanded to create atoms that create stars and galaxies and so on. We are in the center of our visible universe. So the CMB, or the explosion of the Big Bang, was everything, everywhere, potentially infinitely big. It's hard to imagine that it's not infinitely big. It's hard to imagine it's infinitely big. Nothing makes sense for that. But it's potentially infinitely big. We are within this CMB. And the sphere we see around us is basically the time it had, the size of this sphere, the radius of this sphere is basically the age of the universe times the speed of light. This is the further we can go. And this is when you do that, when we see CMB everywhere, because it is the time it took for the photons to reach us. So the CMB was potentially infinitely large but the universe was potentially infinitely long in every direction. It just became bigger. So it's, in a way, from mathematical point of view, it's like you have an infinite number of, if you go to 1, 2, 3, 4, 5, like that, it's infinitely long, right? If I multiply all numbers by 10, so this distance between two numbers is much bigger, and still it's infinitely long. So that's kind of the same, so to me it's kind of the same story for the universe. But yeah, it doesn't help a lot, right?
Fantastic, thank you so much. Just before
Thank you very much.
One bit of housekeeping which I forgot to mention at the start, which I'm mentioning now, and then we'll thank our speaker afterwards. If you enjoy astronomy and you want more, we have an open day here on Saturday the 22nd of March, part of the Cambridge Festival. So from 2 until 6 in the afternoon, the whole department here will be open. There'll be talks and demonstrations and games and activities. So yeah, there's more information on the Cambridge Festival website, or just turn up on Saturday the 22nd for more astronomy. That was the housekeeping I was supposed to do at the start. Now can we thank our speaker again?
Thank you very much for coming.
Thank you. You might get some more questions now. Do you want like a cup of tea or a biscuit or something while you talk?
A tea, yeah, that's very